Hey, this is Leach with Simpson Math, and today we're going to be using technology to answer normal distribution questions. Our first ones we're going to be looking at are going to be this. Using Desmos, Excel, or a graphing calculator, find the percent of observations from the standard normal distribution to satisfy the following statements. So we'll be looking at something like this. Find the probability that z is less than 1.23. Now, in our last lecture, we looked at finding the percent that a value might be less than 1 or less than 2 or greater than 3 or between 0 and 2. Something like that, using what we call the 68, 95, 99.7 rule. Well, 1.23, that's not one of our nice integer values. So that's why we're going to be using technology to help answer this. Throughout this lecture, I'm going to be using Desmos. You are free to use Excel or a graphing calculator as well, but I'll be using Desmos to demonstrate this. But before we dive into these questions, I'm actually going to go back to the 68, 95, 99.7 rule and show you how we can get all those probabilities using Desmos. All right, so here on the right, we have our standard normal distribution, a normally distributed distribution with a mean of 0 and standard deviation of 1. And then our 68, 95, 99.7 rule, or the empirical rule. Let me zoom in on it just a bit. All right, on the left, I have Desmos open. I'm going to tap in the first entry line, and then up pops my entry kind of calculator keyboard. And then I'm going to pick functions. And then normally it starts on trig, but then we're going to need to go to distributions, the DIST, the third one over. And then we will pick normal distributions, the normal dist. So pick normal dist for normal distribution. Notice we have an empty parentheses that we need to type in. It is assuming a mean of 0 and standard deviation of 1, and you can see that it says that in gray underneath, mean equals 0, standard deviation equal 1. And we can modify that if we want to, but I'm going to go ahead and just actually fill in the 0 and 1 because we're going to be working with the standard normal distribution. So I'm going to type in 0 for my mean, comma, and then 1. We're not required, like I said, to type in 0 and 1 if I'm using just 0 and 1, but just to demonstrate that I'm putting the mean and the standard deviation in the parentheses, I'll go ahead and do that. I'm going to press this plus zoom button on the far left, oops, and it zooms in to our distribution so we can see it nice and clear. All right, so there's a normal model, but how do I find the percentages? Well, there's a little check mark box, and I'm going to tick that check mark box. Oh, and if you're keeping track of these directions, I do have them written down in a minute, so you can more just watch this process and not have to worry about writing them down. I have them written down in a minute. So I check this tick mark box so I can find the cumulative probability. Notice that's the CDF, as we talked about last lecture, cumulative distribution function. Right now it's going from negative infinity to positive infinity, and it tells us that it's equal to 1, because all the area underneath this normal model curve adds up to 1. Well, let's just run through our 68, 95, 99.7 rule. So if I have this go from negative 1, so typed in negative 1, to positive 1, notice what's the area under the curve from negative 1 to positive 1? Well, last time we would say, well, oh, that's 68%. It's actually approximately 68%. That empirical rule is a nice approximation for us. It's more exactly 0.682689492137 . So it is about 68%. So it rounds to that 68. So that's why we just say, 68. But it's more precisely this other thing. So if I go from 2 standard deviations down to 2 standard deviations up, that would be going from negative 2 to positive 2. And notice that's about 95%. It's a little bit bigger than 95%. It's actually 95.45%, but about 95%. And if I go from negative 3 to positive 3, then that's 99.7, about, a little bit more precisely, 99.73. And that one is actually pretty close to our approximation we had earlier. Notice we could go from, let's say if I wanted to go from 1 to infinity. So in this first blank, I have a 1, and then I'm going to delete the 3, and then just tap out of it. And notice now it's saying it's going from 1 to infinity. 1 for my minimum, my maximum is infinity. Last time we said that would be about 16%, and it turns out that that's about 15.87%. So 16 is a good approximation. If 2 to infinity should be about 2.5. Let's find out. Well, it's about 2.275. And 3 to infinity is about 0.15. And yep, it's about 0.135. So pretty close. We also found from 0 to infinity is 50%, and that is right on the money, because this is a perfectly symmetric distribution. Now I can also find the area from that I found are -1 to 0. So let's make our minimum be -1 and our maximum be 0. So we're just playing around here, and we see that -1 to 0 is actually just a little bit over that 34%, 34.1%. If I wanted to go from, and it underlines it in red, that's showing that I'm saying my minimum is 2, my maximum is 0, and it did not like that because it's my minimum is bigger than my max, so it turns those underlines red when you have something wrong. So what if I go from -2 to 0? Notice that's about 47%, 48%. But one of our numbers we had written down was -2 to -1. Should be about 13.5, and it is. It's about 13.6. And the last number we wrote down was -3 to -2, and that should be about 2.35. And a little bit more precisely, it's about 2.14%. So there you have it. Those are the more exact values. There's still approximations, but more exact values than our empirical 68, 95, 99.7 rule. All right, so now that we have a little bit more familiarity with this, let's answer some questions that we haven't already done. So let's go back to that letter A. All right, so we're back here looking at example 3, letter A. This time I have Desmos nice and small, so this is sort of kind of what it feels like if you're on a cell phone. It's about that same size, but it does the same thing whether you're on your computer, the tablet, or the phone. So first we're going to be talking about, again, using the standard normal. So just to be clear, if I'm talking about the standard normal distribution, it's a distribution where we're talking about the z-scores that's normally distributed with a mean of 0 and standard deviation of 1. So first, let's talk about the directions. So here's some quick directions about how we get here. So first up, in the graphing calculator function of Desmos, pick functions, and then pick distribution, and then normal distribution. I'll do that one more time real fast. So in the graphing calculator, type in the entry line, pick functions, pick distributions like I'm already at, and then normal distribution. Right? Then input the mean and standard deviation. Here this is 0, 1, mean, 0, mean 0, standard deviation 1. Then it says check the find cumulative property CDF box, so I'll check that box, and then we'll input our lower and upper boundaries, and we'll leave it blank if it's negative infinity or positive infinity. Letter A, we want to find the probability that z is less than 1.23. And so we're going to first draw the picture. So it's always a good idea to draw the picture every time you do one of these. So in my picture, I have my mean labeled at 0 and my standard deviation of 1. And then I'm going to put where 1.23 would be on the scale. So just a reminder, if this is 0, then, and I go up 1 standard deviation, that's 1, that's about 2, that's about 3. So you can be able to just estimate where 1.23 is. So there's our 1.23. So over here on my calculator, I'm going to go from negative infinity, because it's going all the way less than. So I want to go all the way to all the smallest numbers ever, because it's less than 1.23. My biggest is 1.23, so I'm going to type in 1.23. And notice when I do, the shading changes with it, and it goes from negative infinity all the way up to 1.23, and I get 0.89065. And in your notes, I already have included this the entry of what it's going to look like. So this is our answer, that 0.89065. I have a note here that says to round to 4 decimal places, and I've color-coded this box with our directions here. So then just as a final answer, probability that z is less than 1.23 is 89.07%. So this gives us to us as a proportion between 0 and 1. So this is a proportion between 0 and 1. So we should convert this to a percent if it's asking for a percent. So move it over 2 decimal places and we get 89.07%. All right, let's do the next one. Find the probability that z is greater than 1.23. So let's draw our picture. So our picture, it's more or less the mirror image of what we had before. So it's 1.23 is in the same spot, but this time we are shading up instead of shading down because it's greater than 1.23. So I want to find all the area of all the z's that are greater than that 1.23. So what's different about this in the calculator is my smallest number is now 1.23. And notice this, what I have right here, this is not the answer, but I want to show you. I'm going right now, what's in the calculator is from 1.23 all the way up to, not very far, just 1.23. So notice the area under this continuous curve, if I'm wanting to find the area equal to 1.23, that's just 0, right? These lines, this area under a point has no thickness, it has no area. So notice its area is 1.23 if it's the same location, if we're in one spot, because this is continuous. If this was a discrete distribution, there would be a different story. All right, so my minimum is 1.23, and I'm going to go up to infinity. So I'm just going to delete the maximum altogether, and when I tap out of it, you'll notice that there's now a gray infinity. So this is 0.1093, and that's the same thing that I got. So my answer is that the probability that z is greater than 1.23 is 10.93. But I want you to notice something about these two numbers. In terms of probability, they are complements to each other. They're complementary. They both add up to 100%. That's because, remember, the entire area under the normal model adds up to 1 or 100%. So if I find the area less than a point, less than a location, and I compare that to the area greater than that same location, those collectively should add to 1. So I should be able to also have just found the answer by doing 100% minus what I got earlier, and then I would get the same answer of 10.93%. All right, this next one is the probability that z is greater than negative 0.86. I want you to pause the video and try this on your own. All right, welcome back. For this one, again, we draw a picture, and this time I'm starting at a negative 0.86, and I'm finding the area greater than that. So in my calculator, I put in a minimum value of negative 0.86 and left the maximum blank. And when we did, we got about 80.5%. So our final answer was 80.51%. And notice you could have also done a less than here like that if you chose to, right? Because again, those are complementary. So 100% minus a less than would also give us that same answer. All right, next, let's move on to a between question. So this is that z is between negative 2.14 and positive 0.56. So here's what the picture would look like. I want to find the area that z is between negative 2.14 and positive 0.56. So in my calculator, I'm going to go from negative 2.14 to positive 0.56, and I get 69.61. So here's that same input that I have that I had over there. And so then it's the area that is between that is at 69.61%. Right? So that's how you do a between question. I want you to pause the video and try this next one on your own. All right, welcome back. So let's take a look first with our picture. So we start at 0, and we have our standard deviation of 1, mean of 0, standard deviation of 1. And then we're going to go from 1.11 to 2.22, and it's the area in between, so it's just that little piece. So in my calculator, I go from 1.11 to a maximum of 2.22, and when we do, we get about 12.03%. So my final answer is that the probability that I get a z between those two values is 12.03%. Right? And lastly, I want you to do letter F, probability that z is less than 2, and compare this to our 68, 95, 99.7 rule. So this is one you could do by approximating it with that rule, but I want to see if you can do it using the calculator. Pause the video and try it on your own. All right, welcome back. So we have our mean of 0, standard deviation of 1, and we're going up 2 standard deviations, so that's a z-score of 2, and we're finding the area less than that. And so I have it going from negative infinity to 2, and I get about 97.72%. Using the empirical rule, you would have gotten 97.5%. That's just a little bit more accurate with that 0.72 instead of 0.5. So there you have it. So this is how we can use the use Desmos to where you're given x values to then find the percentages. All right, let's move on and work this backwards. All right, so next we're going to use technology to work backwards. So here I'm giving you a percent or a percentile, and you have to tell me the endpoints of these z-scores. So the first question is we're going to find the 30th percentile. So basically, in this normal model, what is the 30th percentile? So we're going to need to change a little bit about what we have set up with our calculator. I think we have some directions right here, so let's check them out. So step 1 is we need to set our normal distribution equal to a letter. I'm going to choose D for distribution. So over here in the calculator, I'm going to actually uncheck that cumulative because we don't need it. And then I'm going to give it a letter. So I'm going to move over to my keyboard and type in a D and go back and say equal to. So now I'm just saying I'm giving this distribution a name. You can have multiple distributions and have them each have their own letter. This is because in the next line I need to refer to this distribution. So I'm going to give it that name. We did this similar with like lists and stuff. So I'm just giving it a name, D. And then in another line, we're going to type our letter. So I'm going to type my D. So I'm going to go back to my keyboard and type a D. And then follow it by a decimal, a period, a dot, whatever you want to call it, but the dot. And then we need to input the inverse CDF. So in mathematics, an inverse function switches the inputs and the outputs. So previously with the CDF, that is a function, it's a cumulative distribution function. When I put in an x value, a percent comes out. So now I'm going to put in a percent, and an x is going to come out. So again, let's press the functions button, and then go to distributions if it's not already, DIST, and then further down the list on the bottom, pick inverse CDF. So inverse CDF of our D distribution, and then the input there, we're going to input in the parentheses a percentile. And we have to input it as a number between 0 and 1. And remember, percentiles, and this is going to be a very important point throughout the rest of the notes. Percentile is area or proportion shading to the left, shading to negative infinity. So wherever our line is that we're drawing, it's what we're looking for. It's less than. So if this is a percentile, I'm asking for what is the 30th percentile. That is the 30th percentile, or a value of 0.3. So I'm going to put in 0.3. So with this value of 0.3, notice this did not update the picture at all. If you wanted to make a picture just to check it, you could turn back on the cumulative probability and type in this z-score of negative 0.5244. So what this inverse CDF equals is a z-score, or an x value in a way, but in this case it's a z-score. So in my maximum, I can type in negative 0.5244, and the more numbers I put in, the closer that the output is to that 30th percentile, or that 0.3. Now I'm not needing to do this every time, but just to show you that if I put in from negative infinity all the way up to negative 0.5244, that would return to me 30% of that graph. So what the inverse CDF does is it goes, oh, well, if you want the 30th percentile, or 0.3, you want to be at a location of negative 0.52 on your D distribution, which is a z-score in this case. So I'm going to turn off that cumulative probability, and let's work through this. So first, as always, let's draw our picture. Here's a tip. When you're drawing the picture with the shading, you can use your knowledge of the 68, 95, 99.7 rule to estimate the location of this 30th percentile. In this case, I know that if I'm at -1 and looking less than, that's 16%. Let me point to it using this graph. If I'm at -1, -1 z-score, and I look for the area less than, that should be 16%. So because of that, I know that the z-score I'm looking for has to be bigger than this line. At the same time, I know that if I'm at 0 and looking less than, that is 50%. So that means I know that it has to be less than the 0 line. So I know it has to be bigger than 1, smaller than the 0. So, and knowing that this less than 1, if less than -1 is 16%. So it's probably a bit close to that, but it actually ends up being actually about halfway. So, but somewhere with a reasonable estimate, draw a line. I'm not going to pull out a ruler or anything on you. So draw a line and say that this is less than, and then go ahead and label that this is the 30%. And then I am looking for my x value, or in this case it's a z. So I've labeled on this one that what I'm looking for, I don't know what it is when I'm just drawing the picture, is this -0.52. So then we do the calculator thing, which we just did. And I've highlighted highlighted our steps and corresponding with my directions, and we get our -0.52. So just to be clear, what this tells us is that the probability that z is less than -0.52, which is 30%. So that tells me that the answer I'm looking for is that z is -0.52. All right, this time, let's find 30% of all observations are greater than z. Greater than z. So let's drive first to our picture. All right, so this is the top 30%. I'm giving you an upper percent. So there's some z value out there where the upper percent is 30%. So here's my 0 and my standard deviation of 1. So this is the upper 30%. Again, I knew that if I'm at 1 and greater than that 16%, so it's a little bit less than that. So draw some line, put down a question mark. And I'm labeling that this is 30%. Now remember about my calculator? I said that the inverse CDF has to be less than, has to be a percentile. This 30% is not a percentile. Remember, percentiles are at whatever location you're talking about, it is percent less than. This 30% is percent greater than. So I need to find the percent less than this unknown value. Well, if the percent above it is 30% and everything adds up to 100%, then the percent less than has to be 70%. So let me come over here and put in instead of 70%, I can type in 0.7. And here I get 0.5244. So here's my input. And what's different about this is it has to be this 0.7. If you type in this 30 percentile, you're going to get what we got last time, which is a -0.5244. I know that this should be positive because I'm on the right side of 0. I'm on the right side of 0. I'm positive. It has to be positive. So in order for this to be positive here, then this would need to be a number bigger than 0.5 because that would be a percentile that would be bigger than 0. So I get this 70 again because this is 100 minus 30. So I put in 0.7. If I typed in 7D, it's going to give me an error. Notice it says undefined right there. It's undefined because this input has to be a number between 0 and 1 inclusive. So if you get undefined, make sure that you have your decimals. So it should be 0.7. So our final answer is that it is z is 0.52. It is no coincidence that these are opposites of each other because this normal model is perfectly symmetric. All right, I want you to pause the video and try the next one on your own. Find the z-score that satisfies this statement. 57.3% of all observations are greater than this unknown z. Pause the video, try this on your own. All right, welcome back. As always, let's start with our picture. So we have a mean of 0, standard deviation of 1, and it's our upper 57.3%. So there's some z, and then I know that it says that there is a percentage of z-scores that are greater than, 57.3% of z-scores are greater than my particular z. So it's upper bound. So in order for me to use the calculator, I need to find the percentile. The percentile in this case would be this unshaded white space. So I'm going to do 100 minus 57.3, and I get 42.7%, or as a decimal, I get 0.427. So I put the 0.427 in my calculator, and I get a negative 0.18. And again, you should think about with this positive negatives, it makes sense for it to be negative because my picture shows that I'm to the left of 0. So as a final answer, I have that z equals negative 0.18. All right, lastly for this video, we're going to find the middle 60%. So we're going to do what I call the middle percent dance for this. So the middle percent dance is this. If I'm doing this physically in front of y'all, I would literally have little hand motions that go with this. It has to do with sort of kind of wax on, wax off, but nonetheless. So I think to myself that everything is 100%. So I know that everything, oops, let me switch tools. Everything is 100%. And I'm looking for the middle 60%. It's very important that we're talking about the middle. If it was just some interval 60, this does not work. It has to be the middle 60%. So if this is the middle 60%, that means that leaves 40% in the wings. So again, everything is 100%. This is 60% in the middle. So 100 minus 60 is 40. So that means collectively in the wings, I have 40%. Well, this distribution is perfectly symmetric. So if I have 40 in each wing, divide that by 2, and I just have 20 in this bottom one, or 20 in this top one. Let me do that again. Everything adds up to 100%. Here in the middle is 60%. 100 minus 60% is 40. So total left over in the wings is 40%. I just need one of those, so I'm going to divide by 2, get rid of one of them, and so this is going to be 20% in this bottom wing. So that's important to note this. And also, again, as a quick check, 20 plus 60 plus 20 is 100%. So I can put in this 20% into my calculator, and I'll get the correct z-score. So let me go ahead and do that. So this is going to be 0.2, and I'll get a z-score of negative 0.84. All right. Additionally, I need to find this value. Well, what's the area less than this? Well, it's 20% and 60% added together, so 80%. So if I do the same thing, I'm going to do my d decimal inverse CDF of 0.8. Notice this time I get a positive 0.84. That is not a coincidence because these numbers are on symmetrical locations of each other. If I fold this distribution in half right here, these two locations would be on top of each other. So really you could just find this 0.2 and then just change the sign for this particular problem. They're just z-scores. So here's a snapshot of my calculator, and then there's my 0.2 that I did earlier, and then if you want to do the 0.8, then you would need to add these two things up. So then just to be clear what my final answer is, I have a lower bound for a z-score, lower boundary of the shaded area, and an upper boundary or upper bound. So my lower bound is that z is negative 0.84, my upper bound is that z is a positive 0.84. And like I said earlier, this is optional as z-scores are opposite of each other. All right, so this concludes this part of the video. In our next video, we're going to be using the same tool, the same technique, the same setup, but instead of it just being random z-scores that we're finding, we're going to be looking for numbers in context. This is actually the more usefulness, final sort of kind of type of normal model problems that we're going to be dealing with. All right, so I'll see you in the next video.